So I removed 2 problems from the homework assignment. They were actually longer problems, and I think you're going to be okay without doing those problems. So you only have 13 problems on this assignment. All right. So a lot of you folks, well, some of you folks started on the homework already, which is good. A couple of problems require a little bit of thought, but you should be able to get through them fairly quickly. Oh, Chase, the homework that's due on Sunday, I'll probably add it. I'll probably change it to Tuesday. It's the chapter 27 homework. You know, I've been lecturing on. It's a really short assignment. They're probably short, but it's on Ohm's law. So it's a short assignment. It's really going a little bit ahead of the game in that chapter, but in the book. But it helps with the multi-move quiz. That's why I did it. Okay. So, okay. Let me see if I missed any question. And by the way, if I don't pin myself every lecture, just remind me. I just want to make sure I didn't miss anybody else's questions. Okay. All right. So I wanted to show you a demonstration video because I can't do it here on equipotentials, and it was one that Tyler made for us. I'd say, well, I guess last year. So let me show you this video on YouTube. Let me find the video, and then let me put it on screen. Give me a second. Okay, so this is a video of a Van de Graaff generator, and we're going to have Tyler's going to bring a neon bulb, and what's he going to do is he's going to put the neon bulb tangent to one of the equipotential lines, and then parallel to the one of the field lines, so you get to see what happens.
Hey everyone, today we're going to be talking about equipotentials. In front is a running Van de Graaff generator, and here is a neon light bulb attached to a non-conductive meter stick. So we're going to look at the orientation and watch the light bulb. You can see the bulb lighting up, and that's because we have a different potential between the two ends. Now I'm going to rotate it, and now there is no difference in potential. So the two ends are generating a different potential.
Okay. So, just give me 1 second. So what you saw in the example is when he put the lamp perpendicular to or tangent to one of the equipotentials, then there was no potential difference across the bulb, and so it wouldn't light up. And so when he rotated the neon bulb so that it was along one of the field lines, then there was a potential difference across the ends of the bulb, and that caused the light to glow, because that potential difference means you have an electric field. Okay, so what I'm going to do today is I'm going to finish up the chapter, talk about calculating the electric potential, and I'm going to do some examples. All right, so let me go to my PowerPoint. And I'm going to do the calculations for discrete cases and continuous cases. So basically all we're going to be doing is calculating or doing different examples of equipotentials. All right. I'm going to do the easy problem first. I'm going to do the discrete case. Okay? If we have a discrete set of charges, how do we calculate the total electrical potential? Now, some of you folks have already started on the homework, so you guys kind of know how this is going to work here. So I want to use the concepts. Just a second, sorry. I want to use the concepts we've discussed already to calculate the electric potential for that charge distribution. Okay. And because electric potential is a scalar and it obeys the principle of linear superposition, this is actually not that hard a problem. Let me draw a picture. There's one charge here. And one charge here. Okay, this is x equals minus a. And this is x equals 0. We want to calculate at some point p here a distance y from the x-axis. And we know that for a point charge, we did this the other day, that v for a point charge is k q over r. And so all I need to do to calculate the potential here is calculate the potential due to this charge and calculate the potential due to that charge. That's all I got to do. So my total potential, I'll just use v sub t, is going to be the potential due to this one, plus the potential due to this one. And so the distance now from here to here, I use the Pythagorean theorem. And I'm done. In fact, if I want to factor out just for fun, I can write it like this. That's it. That's all I have to do. Now, one fun question I can ask is, can I calculate the electric field at this point? And you guys already know how to do that. You guys already know how to calculate the electric field at this point. We did this in chapter 23. But we can also use this equation. E is the gradient of the electrical potential to calculate V. So in fact, now you can calculate it two different ways, and you can use one to check the other. Yes, Chase, this is not the magnitude. Good question. Oh, it's a Q, sorry. Okay, we don't put the magnitude in here anymore, because I'm not writing this as a vector, it's actually a scalar. Okay? All right, so let's calculate the electric field. This thing is going to have an electric field component at this point in the x direction and the y direction. Why? Because the electric field due to this charge at this point points downward, and the electric field due to this charge at this point is directed that way. So this thing is going to have x and y components. And so what I need to do is I need to calculate the derivative of this function with respect to x. But here's a problem. I've already substituted my value of x in here. So let me write v in general. I need to write v this way. before I can take the derivative. And then I'll substitute the value of A. And now I want to calculate the x component of the electric field. Remember what this is. And I don't care about the z component because there's no z's in here. Okay. So I'm going to take the derivative of the electric potential with respect to x. So if I take the derivative with respect to x, what am I going to get? I'm going to get k, q, and I take the negative derivative, and I'm going to get x squared plus y squared and 2 halves. And then another minus sign will come out. Is that okay? And then the y component, let me put a semicolon here. He said y, I'm not going to have enough room to put, he said y, I'm sorry. He said y is going to be minus the derivative of that expression with respect to y. So I'm going to get minus k, q. So when I take a derivative, the square root drops a 1/2. It does, isn't it? You're right, the square root drops a 1/2. What about when you take the derivative of x squared?
Yeah, it drops to 2.
Okay, yeah. I know I did 2 steps at once, sorry. Okay. So the next thing then, I get to substitute back my value of A. I don't want to rewrite everything, so I'm going to substitute my value of A in here. Because this is calculated at the location A. And so my total electric field is this. That's it. That's all you got to do. And yeah, I did skip a couple steps because you guys, some of you folks are worrying about the 1/2. I apologize. I did 2 steps at once. Okay, so you can actually calculate the electric field at this point just by calculating and taking derivatives. And of course, you just use whatever method you like if you have a charge distribution like that. So these types of problems are fairly straightforward. It just gets tedious when you have like 10 charges, right? Doing 10 charges like this would be very tedious. Okay, so let's do something a little more complicated. Let's do something involving a continuous charge distribution, and it turns out these are not that bad either. The reason why is because we don't need to calculate our hat. This is a scalar, so this is going to require one less step than the electric field calculation. So if I have a continuous distribution of charge, about a week and a half ago, I drew a similar picture like this. And I want to calculate the electric potential at that point P. Maybe I should make it a dot. I'll use an X there. That's a location in space, and if I had some device that measured the electrical potential at different regions, I would put it at this point and see what the device read. Okay. What I have to do is I have to take this charge distribution, whatever it is, and I have to break it up into a bunch of little charges, dq's, and calculate the electric potential due to this dq at this point, whatever the r is. Remember, the r is the magnitude of the vector that points from the source to the point at which you're calculating the potential. Okay. If I do it for all dq's, they make up this system. And so that means that I have to sum over all of them. Of course, if they're infinitesimal slices, then or pieces, then I have to do an integration. So I take v is the integral of k dq over r. So let's think about where this comes from. This comes from the fact that the field, it comes from the fact that the electric potential for a point charge is k q over r. This comes from the fact that the electric potential due to a point charge is kq over r. So what this means is that we're assuming already that the electric potential is 0 to infinity. Okay? When doing this, using this methodology, we're assuming that the electric potential is 0 to infinity. We're breaking up this charge distribution into a bunch of teeny tiny point charges. We're going to see we're going to run into problems for charge distributions that are very large. We won't be able to use this for charge distributions that are very large, like an infinite plane, because the electric potential won't be 0 at infinity. Well, it's not necessarily 0 at infinity. Okay? Because an infinite plane has an infinite amount of charge. Okay, so what is our process for calculating the electric potential at some point B for some charge distribution? Basically, you got to find your expression for dq and your expression for r. You integrate. That's it. That's all you got to do. There's one less step here. And we've done the calculations for the electric field. You are now used to it. You get a worksheet for the electric field already. Most of you did fairly well on it. This should be more straightforward because there's no r hat you have to determine. Okay? So I do list this in your notes. Choose a coordinate system, write your expression for dq, determine your r, put it all together and integrate. And again, like what I said before, this is only valid for charge distributions that are finite in size. If the charge distribution is very large, like an infinite plane or a long rod, this is not going to work. But there is a better way to do the calculation, which I will show you today too. Okay? All right. So let's do this example. I want to calculate the electric potential as a function of z at a point on the x-axis, not of a ring, The rings are actually very easy. But a circular disk of total charge Q, and let's make the disk uniformly charged so the math is a little bit easier. Okay.
Professor,
Yes.
just before we start this problem, like in the previous problem, should there be a negative for the j hat component?
For this one?
Yes, because like there was a negative before the gradient.
I erased it, but I distributed it through.
Yeah, but like there was a negative for the e sub y itself, right? Like there were two negatives. One was already there, and then one comes from the formula.
Yeah, so you're talking about this one then?
On the outside, in front of the k, q.
Well, this one, there was a negative here, there was a negative out here, they canceled.
Yes, and then there is a negative from the formula, right?
Yeah, the negative from your formula, right? So if you take the derivative,
Is the e sub y, the negative in it, is that from the formula you wrote in there? For the first line?
this one, yeah.
No, for
this one you mean?
Yes.
Yeah. So this and this cancel.
Okay, so that is from the formula.
Yeah.
Okay.
Professor?
Yeah.
Also, just real quick, if you could move the camera down just a little bit.
Oh yeah, you're right, thank you.
Thank you.
Yeah, let me change the magnification too, that's probably the problem too. That better?
Yes, thank you so much.
Okay, sorry about that. Okay. All right, so let's do the disk. And I know green doesn't show up very well, but I'm drawing green because I want to show you the random stuff that I'm going to draw for it. So here's my coordinate system. So I guess I'll do x here, y here, and z here. That's a right-handed coordinate system. I can also do z here, x here, and y here. It's the same thing. It's a right-handed coordinate system. Okay. We want to find the field at some point up here. I don't have the field, though, it's the potential. So what I need to do is, and this is a solid, disk. I don't know if that's a good picture, I apologize. I want to break it up into rings of radius r. Okay, and thickness dr. So this is a ring of radius r and thickness dr. So, and it's uniformly charged. So what's my dq? Well, it's going to be our sigma dA. If it's uniformly charged, then the charge density is the total charge divided by the area of this thing. What's my element of area? Well, if I take this ring and I cut it out with a pair of scissors and I'm able to straighten it out, imagine I can straighten it out. And the radius of this thing is 2 pi r, and the thickness is dr. And so the area is going to be 2 pi r dr. Just imagine breaking this up into a bunch of teeny tiny rings, like like imagine an old tree with a lot of rings, okay? And you want to consider the amount of charge on each one of those rings. And so this represents the amount of charge on each one of those rings. And along any of those rings, the potential is the same because the distance from anywhere on the ring to this point P is the same all the way around. This distance is the same all the way around. And so, for that ring, then we can write down an expression for dV. Now the question is, what is the distance from here, point P, to the ring? R, which is the magnitude of the vector that goes from here on the disk to the point P. That's going to be the square root of r squared plus z squared. Okay? So then our dV is k dq over r. Let me erase some stuff here. Okay, dq is this. And r is that. And then I integrate. You might want to cancel out some stuff though before you integrate, because we have the ability to cancel out stuff, so I can get rid of a pi there. Right? So maybe before I integrate, integrate over all the rings that make up this thing. Let's see. I can see this.
Professor,
Yeah.
is that a z under the root, not an a?
Yes, it is. Sorry about that. Okay. Are we okay up to here?
You dropped the a squared.
All right, thank you. All right, how about now?
Looks great.
That's great. Okay, great. Sorry about that. All right, so that's a U sub, right? If you integrate that, that's a U sub. That's an easy integral to do. I hope you find that an easy one to evaluate. I mean, really, to me, the most important part of the problem is getting to this point. Right, the rest of it is just a basic integral. So this integral is not that hard. Anyway, I had all this stuff written in your notes, but let me get to the next slide. So we have this integral. Use U sub, perform the integral, and what you do, I'm not going to bore you with the details of the integral, okay? What you get is this, 2kq over a squared times the square root of u squared plus a squared minus the absolute value of z. Okay? Don't tell you, the math professor, I skipped all the steps. All right? But on the test, you should be able to do this because this is a U sub. So what are questions one can ask? Well, what if you're really far away? What if you're really far away?
Then a looks like 0, right?
Yeah, so you essentially get like that of Kind of like a point charge, right?
Yeah.
Okay. And one of the things you can do, this thing is very small compared to this. So you can almost say, you can see the KQ over A squared term. You can ask questions about what is potential real close, but then you have to use approximation methods. So you have to factor out one of the two depending on which one's bigger. When you're close or real far away, then you find the number of expansion. Can I calculate the electric field from this? Can I calculate the electric field from this? Yeah, in fact, I only need to take one derivative. Which derivative would I need to take?
Just with respect to Z.
Yeah, why only with respect to Z?
Because the electric field doesn't have any X or Y components, so it'd just be zero.
Yeah, they all cancel out. So all I have to do is calculate the derivative with respect to Z, and then I get the electric field. Chase, you said, can't you do what you did last time? Oh yeah. That's I get it. Okay. Yeah. So
Does the particle
I'm sorry.
Does the partial derivative formula always work to find the electric field from the electrical potential?
Yeah, because it's a general expression because we came up with the expression for V from the electric field, so that always works.
Gotcha. Okay.
Yeah, it's very general. So yeah, if you know V, you can get E right away. It's not as physical, but it works. Sometimes the reason why I asked about calculating the electric field, because some students will actually take derivative with respect to R, and that's not going to work because the field in the R direction is going to be zero. So some of you guys already said that, so that's good. If the charge density was not uniform, then you'd have a term inside here that would take into account the charge density. Okay. So if you plot the electric field and the electric potential as a function of Z, you get those two. Let me make my screen display bigger. These two represent graphs of the electric field and the electric potential plotted along the as a function of Z. So the first graph, the top graph, is the electric potential. So it's that function that I had on the board. Okay, the bottom function here, this one right here, that's what I graphed. That's the electric potential. And it's symmetric about both sides of the charge distribution, the disk, because it's a positively charged disk. Okay. Now, the electric field, the electric field, if you notice, has a discontinuity at Z equals 0. The electric potential does not. So this is an important thing I'm going to say now. It's very important. The electric field can always be discontinuous. There's no problem with that. The electric field can be discontinuous across the boundary. The electric potential cannot be discontinuous. It has to be continuous. Why? Well, the electric field is the derivative of the electric potential. So how can you take the derivative of something that's not continuous? Right? That top function has to be continuous. Even though at the peak there, the derivative changes, the derivative is not continuous, the function itself has to be continuous. So it's important to remember, maybe I'll write it down. electric potential must be continuous as boundaries. The electric field doesn't have to be. In order to get the electric field, I got to take the derivative of this. So otherwise, I get something non-physical for the electric field. I'd get an infinite electric field. That means it would be under influence of an infinite force. So it's completely not physical. Okay? So this has to be true at all boundaries. So this is one of the first problems you encounter where you're dealing with the boundary. Yeah, the discontinuity in the electric field comes from the sharp point. Right, because you can tell a slope changes at the sharp point, right? Okay. And this is important. In this course, you don't spend a lot of time worrying about boundaries, let's just say boundaries. But when you take an advanced course in this field, in the junior level, you basically do the same problems, except you got to worry about how to deal with the boundaries. And it becomes complicated, actually. You have to use some fancy techniques to solve problems with boundaries. And this idea, problems involving boundaries, not only occurs in this subject, but if you take 215, you talk about a wave crossing the boundary, you have to consider what happens at the boundary. The waves have to be continuous across the boundary also. Okay. Let's do one more example. This is related to one I have in the video. So we have a long rod, or just a rod, it shouldn't be long. A rod of length L that lies along the x-axis. Okay. It has non-uniform charge density. We want to find the electric potential at this point. That's A from the edge. And this distance is L. And this is point P. I guess I should make it X. Okay? So, first question is, what's our dq? dq is going to be, well, I got to break this up into little pieces. Length dx. This dq is going to be lambda dx, which is lambda naught x dx. And we can figure out lambda naught because we know the total charge on this thing. This is like one of the exercises you did in the homework. Okay? So this is like one of the homework problems we did. So then I can write it this way. And then the distance from this element to this point, this distance is x here. This distance is L plus A minus x. So R is L plus A minus x. Then our dv is K dq. Oh, there's the dq. Over R. And so V then is going to be the integral over the whole length of the rod That's it. So once you're at this point, then you're okay, and the rest of it just doing an integral. And so then v ends up being, if you work out the integral, I'm not going to bore you with the details of the integral. I'll just give you the final answer. Look at this. Okay. Now, what if you wanted to find the electric field?
You take the partial derivative.
Yeah. But I would call this an x. I would put the x in because this represents it at a particular point. So I would write this as a function of x. Take the derivative. I'm just being very formal. Take the derivative with respect to x and then put it back in, and you should get the same electric field as in the example I did in the video. Okay. So what I want to do now is show you a different way to calculate V. Actually, the different way that I'm going to show you works for every single case. This only works for charge distributions that are finite in extent. Okay. And yet, Chase, this problem is easier than a disk. So this is the most general way of calculating the electric potential due to a charge distribution, and it really comes from using our equation for delta V.
Professor?
Yes.
Can you show how we would see the equation when A is very large compared to L?
Well, when A is very large, I would rewrite this. I don't have time to do it now, but I can do this. So I would write it like this, and then I would write an expansion for this. I would look up the way to expand this. You do Taylor expansion about 1. And then simplify. You would keep the first term, the first non-zero term in the expansion, and then you'd see what happens. Is that okay?
Yes.
So if you write it like this, because then you can expand it, because then this term is going to be small if you make A big, right?
Yes.
Because those expansions are based on this term being small.
Mm-hmm.
I heard
Are you talking about?
Yeah, he is.
Okay, thank you.
What was the question?
I was just asking if you were talking about the power series.
Yeah, power series. Right, you can expand this in the power series. Anytime you have something like this where A is, the second term here is like really small, you can always expand in a power series. And then what you do is you don't keep all terms, you just keep the first term that gives you something that's non-zero in parentheses.
Thank you.
Okay, sure. That's a trick you learn, and physicists use that a lot. Okay. All right, so using this method, like I said, this method works in every case, but you have to know the expression for the electric field. And it came from the concept of looking at the work done on the charge. That's how we first came up with this idea. And really, it works in every case, but it's really needed if the charge distribution is not finite in extent, like an infinite plane or a wire, a long wire, or a long cylinder. It is more general than our delta V equals K dQ over R, because guess where the delta V equal K dQ over R comes from? It came from this.
The electric field of a point charge.
Yeah, right. It came from the electric field of a point charge, but it came from integrating the electric field, right? I put the equation for the electric field with the point charge in here and integrated to get that expression you see in the slide. And then we said, oh, let's let v equals 0 definitively. Here I can let v equals 0 wherever I want. Okay. So like I said before, it's really related to the amount of work required to move a charge between 2 points. But that's how we came up with the definition of delta V. Remember that V is always known up to some sort of arbitrary constant, so that allows us to choose a 0, a reference point.
Professor?
Yeah.
Can you somehow change your mic because sometimes I cannot hear what you say?
Oh, you know what happened? I think my mic got unplugged. That's why. Sorry about that. Okay, my mic is plugged in now. Sorry. My mic was not plugged into the computer. I didn't notice that.
Okay.
You can hear better now?
Yes.
Okay. Sorry about that. I for some reason I didn't notice that it wasn't plugged in. Yeah, if you use the computer mic, it's not always very good. Okay. So I want to calculate the electric potential for a uniformly charged sphere of radius r. Okay. So I'm going to use this idea. You can see the. So a couple of things. I want to write down the electric field outside the sphere and inside the sphere. So I have a uniformly charged sphere. This is a solid sphere. Total charge Q. Okay. The electric field outside the sphere is that. The electric field inside the sphere is going to be given this way. I don't want to derive this, that's why I'm giving it to you, okay? We talked about this. Actually, when I did the problem with the concentric spheres, I actually derived this equation. And you might not remember it. You remember that one?
Professor?
Yeah.
Should that be a r squared?
Oh, yes. Thank you. Okay. Thank you. And the charge distribution is positive, so the electric field points away from the sphere. Electric field points this way. Okay. So I want to find V everywhere. So notice my electric field has two different expressions to describe it, one for inside and one for outside. All right? So we actually have a bound. This is what you would call a boundary value problem. So this is how you would do it. I would actually start from the outside. I would say, okay, I have a sphere. I want to calculate the electric potential at this point P outside the sphere. And yeah, it acts like a point charge when you're outside the sphere. And I want to use that equation. And so what I want to do is say, okay, I want to get delta V is minus the integral of E dot ds. And I want to integrate between 2 points. Okay, A and B. So this gives me V sub B minus V sub A. I'm always going to integrate outward. In other words, the direction of this is outward. Okay. I'm always going to, my unit vector for ds always points that way. These limits will tell me whether I'm going inward or outward. Because if I do it twice, I'm going to get two negative signs. So my ds is always going to point outward, or my dr will always point outward. Okay. But whether I integrate from here to here or from here to here will be determined by how I put the limits here. So let me put my expression for the electric field. The only thing that's going to contribute to electric field is the component that's parallel to this one. And that's going to be V sub B minus V sub A. In order for me to find the electric potential at some point R away from the sphere, I need to know the electric potential somewhere. I have to define the electric potential somewhere. Okay? Let me take a look. Okay. So I know, and this thing is not, this is not infinitely big, so I can still define the electric potential to be 0 at infinity. So I'm going to choose A to be at infinity. That means this is going to be infinity. And then I'm going to choose point B to be R. Okay?
Hey, Professor, I'm going to summarize the conversation that was happening in chat. Is it possible to use like a center of charge the same way you do like a center of mass?
For a sphere, yes.
Only for a sphere?
Only for a sphere because of its symmetry. You can't do it for any other distribution just because of the symmetry. Because the point charge has the same symmetry as the sphere. That's why.
But can't you find like the center of mass of a non-uniform cube or something, and then treat the gravitational field as coming from that point, or no?
No, because the field's non-uniform. Right. The field depends on 1 over r too, right?
Right.
All right. Your center of mass is a little bit different because you're finding the average position of the mass.
So the reason's like because the gravity, that whole thing is like uniform, I guess, or electric charge isn't.
If we were calculating for the center of mass works for calculating torques, right? If you want to calculate torque, you pretend the mass is concentrated at the center, but you can't do that for calculating gravitational fields. Because each piece that makes up the object contributes differently.
Oh, okay, thanks.
There is no center of electric field, or there is no center of gravitational field concept. Okay, so what does this integral give us? K, Q, and what should I have done? If I were in math class, my math professor, what would my math professor say to me?
Take the limit.
What is it?
A substitute variable and then take the limit.
Like that?
No. I thought we were taking the limit and then doing the integral.
Oh, but you can do this. These are called dummy variables.
Okay.
Right?
We thought something
cheating.
else.
But that's what you can do. So V at infinity is 0, and then the bottom limit is 0, so I get V sub r is K
Q over R. That's it. It behaves like a point charge. So, okay, so that's fine. It behaves like a point charge. Now, when you're inside here, I got to use the same methodology going inside, and the reason why is because the electric field here and the electric field here are different. You don't have the same value for electric field inside here as you do outside here. So this is what I'm going to do. I'm going to say, okay, I'm inside the sphere, and I want to calculate the electric potential inside the sphere as a function of R. So I want to go somewhere inside some distance R away. So this is for R greater than or equal to big R. I want to go inside the sphere. So now I'm going to change this. My equation for the electric field is given by that equation. It's still in the R hat direction. And granted, this is not a hard integral to do, right? Now, what I'm going to choose for my limits, that's the next question. Let me put v sub b and v sub a before I go on. What do I choose for my limits? Well, my final limit is going to be someplace inside the sphere. Isn't that true?
Mm-hmm.
I mean, I should put some location inside the sphere. So let me call this R. Okay, I got to make these dummy variables again. What's this limit going to be? I got to choose a point where I know what the field is.
0.
I can't, but I'm sorry, the potential is. But remember, this field is not valid out here.
On the surface?
On the surface. The field, this equation is valid on the surface. I can't put 0 here, right? Because I don't know what the electric potential is going to be here, and I don't know what's going to be out here. I mean, I can't use anything out here. So I can use something on the surface. Because I know the electric potential has to be continuous across the surface. So V in the surface.
Really quick, why don't we know the electrical potential at the origin?
What do you think it should be?
I don't know. I guess that
We
answers my question. Yeah, I have no clue.
Yeah. So I'm going to use the potential at the surface. And so I'm going to put this here and this here, and then make this, I'll make it a purple R. Yeah, I don't know what it is. I don't know what it is at the center yet. I have no way of knowing. But I know for sure I know for sure what it is on the surface, because I know this has to be continuous on the surface. Okay, so this is KQ over R. So let me do this. I dropped the minus sign, didn't I? So what does this integral give me? It's going to give me R squared over 2 minus big R squared. Look okay? Oops, I messed up. That's this. Then I bring this to the other side of the equation. You don't mind if I just erase and move it over, because I want to save board space. Is that okay? You guys have to probably rewrite everything. Well, I'm going to take this guy, this thing over here, and put it here. And you'll see this term and this term will give me a 3/2. So I'll get the following. Let me check my math here. Okay. You okay with that? I can rewrite it this way. Notice the electric field is linear inside, but the electric potential is quadratic inside. And so if you plotted the electric potential, if you called the value at R equals 0, so V at R equals 0 is going to be what? This is the value at R equals 0. We had no way of knowing what that is, right? We had no way of knowing what that is. We can call it V naught. Because I always ask that question, what's V at the origin? It's this. Okay. And it turns out this is the maximum value. And so when you plot the electric potential, it starts here and then decreases. And then when you get to the surface, it goes as 1 over R. So inside, it's defined by this equation. Outside is defined by this equation. So let me write down my final answer for the electric potential everywhere.
So to find V at the origin, it's kind of like going back and finding the initial condition. For like
say that again.
Going and finding V at the origin is kind of like going back and finding the initial condition.
Yeah, kind of.
Like when you kind of find. Go ahead.
I mean, I mean, you can phrase it that way, but it's not really. I mean, usually when you talk about initial conditions, you're talking about something at t equals 0. But this is a static case.
Right. Okay. Yeah.
So we'll write V equals KQ over R, where R greater than or equal to R, and it's equal to KQ over 2R cubed. So that would be my answer. And there's your graph. So let's do one more. I'm getting close to the end of time. And then I kind of wanted to talk about, after this example, the next thing I'm going to talk about is not really on the exam, but it's important for the next chapter. So let's say I have concentric cylinders. Okay? One of radius A, other radius B, and you connect them to a power supply. When you do that, one will be negatively charged and one will be positively charged. They'll have equal and opposite charges. In this particular case, we're going to look at the charge per unit of length because these are infinitely long. So these are infinitely long shells. You can imagine this being a long wire with a shielding around it, coaxial cable. So this problem actually has practical uses if you're studying electronics and you're looking at very small signals. So what's the field outside that? What's the field out here? If I use Gauss's law, I chose a big cylinder out here. What would be the field out here?
Does it just look like a point charge?
Not even. You have a negative charge here and a positive charge here.
Oh, so is it just zero?
It's zero. The field outside is zero. The field in here is zero. Okay, these are just hollow cylinders. And so the only field that's non-zero is in between here. And it's due to this charge per unit length. And we did this before. The electric field is equal to K lambda over r in the r hat direction. And in fact, it's going to be pointed inward. Okay. Again, you can get this using Gauss's law. I mean, we did this problem. The field due to a wire. I mean, this is essentially, when you're outside this thing, it's like a wire, okay? So I want to calculate the electric potential in between these two. Some point in between, some point here, like let's say R. So I want to use delta V is minus the integral of E dot ds. And I can only do it this way. And the reason why is the only way I can do it this way is because this thing is infinitely long. What's nice here is the two minus signs will cancel. The only part that contributes is the one in the r hat direction. The integral is independent of the path. Otherwise, we wouldn't be able to define a delta V. Okay, so our delta V then is V sub B minus V sub A. And it's going to be the integral of A to B of this thing. All right, so if this is a power supply, I usually know, actually, I actually know what the potential is on both of them. So let's say I know the voltage on the outer one. Okay? So if I know the voltage on the outer one, if I know the voltage here, okay, if I know that, then I'm going to call this R, I'm going to call this little b.
Professor?
Yeah.
So is the voltage of the outer shell the same as that of the power supply?
Yes. Right. If I mean, I can make this V sub B and that's zero, or I can make this V sub B and this some other value. It depends.
Okay.
But let's say I know what it is based on the power supply. Mm-hmm. Okay. And now, and we're gonna. I mean, it all depends on how we reference the power supply.
Okay.
So now, when I integrate this, what do I get? The integral of 1 over r is what?
Minus 1 over r squared.
No, it's natural log, right?
Oh, okay. Never mind. Okay. Oh,
That's it then, right? So v sub r,
Hey, Professor, where did lambda go?
I'm sorry?
Where did a lambda go?
I forgot to write it. Thank you.
It was
So that's it. I'm done. Suppose I know v sub b and v sub a. So suppose I know actually, usually what I know is v sub b minus v sub a. Suppose I know the difference between those two. Then v sub a, v at a, is going to be v sub b plus 2k lambda natural log of a over b. If I know these two, or I know delta v, then I can solve for lambda. So v sub a minus v sub b equal delta v is equal to 2k lambda natural log of a over b. And so lambda is equal to delta v over 2k natural log of a over b. Now, if I wanted to know the amount of charge, this is the charge per unit length, but if I wanted to know the charge per delta V, because that's going to give me an indication of how much charge I can put on the plates, on the cylinders, then I get the following. This tells me how much charge I can put on the cylinders. Let me rephrase that. This tells me how much charge I will be able to put on the cylinders given a delta V. This is called capacitance. This is what we're going to talk about in the next chapter. The whole chapter is about calculating the ratio, this ratio. Well, it's a little bit more than that, but that's how you calculate it. So this is the capacitance of two concentric cylinders. But capacitance is defined to be a positive number, and so you always got to take the absolute value of this. So we'll talk about that. We'll talk about this on Tuesday. So this really leads into the next chapter right away. Okay? So you already know how to find the capacitance of two concentric cylinders. They're actually not that hard problems. You're just adding one little equation from this chapter. Okay, so I finished everything, and so let me look at the question. Where did the dr come from? Are you talking about this, Chase? Now, which dr are you referring to? The first one? Yeah, so one of the things to remember is that this ds has a component in the r hat direction and then another component. Now, if you took 205, you would know that this would be the theta hat direction. Okay, this one never contributes, only this one contributes to the dot product. So this dotted with that gives you your dr. Is that okay? Okay. All right. So I just want to say a few closing things regarding this chapter, and maybe I'll go a few minutes over. I hope you're okay with that. There are a couple little topics that are going to be of importance in the next chapter, and one of them is this. Suppose I take two spheres. They have some initial charge Q1 and Q2. This has radius R1 and R2. And the math is easy for this problem, but a lot of times the concept is hard for students to understand. But mathematically, it's an easy problem. So what happens, and let's assume they're kind of far away from each other. What happens if I take a conducting wire and connect them together? What happens?
Charge flow
Charge flow. How long will a charge flow?
till equilibrium.
Yeah, so charge will flow. So charge flows until equilibrium reached. What does that mean?
The net charge is 0 in the wire.
When what?
Is the net charge 0 in the wire?
Yeah, that one's hard to say. I mean,
When both charges are equal.
not when both charges are equal, because they have different size. If they had the same equal charge, the potential here and the potential here would be different. And if you have a potential here and a potential here be different, then charge has to flow.
So it's like charge per volume then? When
No,
that's
but
equal?
what has to be the same is the potentials have to be the same. So charge flows until V1 final equals V2 final. In other words, when you connect them together by a wire, charge will rearrange itself until the whole system is one equal potential. They're conductors, right? And isn't the potential on the surface of a conductor the same everywhere? Because we talked about this the other day. The surface of all conductors form equal potential. So when you connect these two together, they form an equal potential surface. So charge flows until K Q1 final over R1 equals K Q2 final over R2. How do I find Q1 final and Q2 final? Because I have one equation and two unknowns.
But we know the total charge, right?
Yeah, I started with Q1 and Q2. That's got to be equal to Q1 final plus Q2 final. Because they ain't going to go anywhere else. I'm not going to jump off the sphere. Of course, if we have enough charge, I guess it will. But that's it. So Q1 plus Q2 initial has to be equal to Q1 plus Q2 final. You have two equations, two unknowns. The math is easy. I actually solved the entire problem in your notes. So the fields will be different at the end. The fields on each one of these things will be different, but the electrical potentials will be the same.
Professor?
Yes.
Is this the same as when you told that there is more electric field at sharp points?
Yeah, yes, you're right. So I can use this to show that the electric field is higher at sharper points because this one will have a higher electric field. And in fact, in the notes, I actually do that example. In fact, let me show you. And then it's not rigorous. I want to say a couple more things. So I go through it and basically using the same argument, this particular problem. When I have time, I usually go over it, but this shows you that the electric field is is greater at smaller radii, sharper points. But that was very insightful to say this is the same thing. I mean, what you said is the same thing for my example. Okay. So you helped me go through really two interesting topics at once here. Now, the other thing, and these are all small things I usually talk about, and I alluded to, is that the electric field, since the electric field in the conductor is zero, then the electric field, the electric potential inside the conductor is constant. It's not zero. The electric field inside a conductor is constant, but not zero. And this kind of shows you in general that the surface of a conductor forms an equipotential. Because delta V will be zero inside the potential. That means that the potential has to be everywhere. Oops. The potential everywhere has to be the same. And for a conductor, V looks like that. Now, the graph I have here is the graph of the electric field for a spherical conductor. So outside the conductor really represents the field due to a sphere, but inside the conductor just shows, not the field, the electric potential, sorry. Okay. Inside the conductor, all conductors behave the same. It's constant. It's a horizontal line. V is a function of R. So V is a function of R. Inside the conductor is a horizontal line. Outside, it depends on the shape of the conductor. In this particular example, it's a sphere, so it goes as 1 over R. Okay.
Hey, Professor.
Yeah, well, I'll get to your question in a second. And there's the electric field, inside and outside the conductor. Go ahead.
So I'm trying to, maybe this isn't a good idea, but I'm trying to draw an analogy between, or a connection between this and like a similar thing for gravity, because so the change in potential, in electric potential, is just the change in kinetic energy divided by charge, right? It's like a change in change in potential energy per unit charge.
Yeah.
So if I have the gravity equivalent would be a change in potential energy per unit mass, right?
Correct. Yeah.
So if I have a change in potential energy per unit mass, right, like it's non-zero, does that necessarily imply that the thing is going to move the same way that it implies that there's going to be an electric, like, do you see what I'm saying? Like, I'm trying and find a more physical analog.
Yeah, it means
what does that mean?
It means there's a gravitational field. If the potential energy, if the potential energy per unit mass varies over a region of space, that means you have a field. And yeah, work will be done on the object if you put it in that region of space.
Right, but if okay.
And we spend very little time talking about the potential due to the gravitational potential. But you can define one. Sometimes you'll see it. It's very rare that's discussed.
I'm just trying to think of a more physical way to think of the change in electric potential.
Well, just like energy, electric potential is pretty abstract, because energy is very abstract, right? I mean, you can't touch it, can't see it, right?
Yeah.
Whether you're talking about mechanical energy or electrical energy, or whether you're talking about gravitational potential and electric potential, they're going to be abstract concepts. So yeah, they're hard to grasp. That's why people like Faraday come up with the ideas of equal potentials and not equal potentials, but field lines, because they are
Right.
abstract. Okay, I think I was going to show you one more little thing, but I think that's it then. I don't think I need to show you anything else. Oh yeah, this one. The field inside an empty cavity. Okay, so you have an empty cavity that you see like that. This is a small thing that they talk about in the book. I only talk about it when I have time, but I have time now, I guess. So if the field inside the cavity of a conductor is 0, and the only way you can prove that is to show that when you integrate the electric field over a path, you're supposed to get 0 because the conductor forms a equal potential. So no matter what path you take, the integral has to be 0 between points A and B, which means that inside the cavity of the conductor can't be any field. So that's a small little thing that discussed in your book. But really, I'm done with everything in this chapter. The problem of charge sharing that I showed you on the board. Oops. Hold on a second. The problem that I showed you in charge sharing that you see on the board, that's going to be very important when we talk about charges moving in a wire, especially with capacitors. The one thing that you'll notice here and this is completely solved in your notes, by the way, but the one thing you'll notice is when charge flows, the amount of charge that's gained by one conductor is always going to be equal to the amount of charge that's lost by the other. Okay. So I'm going to stop here. So tomorrow, I have office hours from 4:30 to 6, but I can go longer. Okay. Yeah, Dane, that was for the multimeter. The multimeter lab that we're doing is due on the 9th. When you look at the document, it says multimeter quiz. It's just a skill demonstration. What? Okay, yeah, and sometimes it's called, and we've always had a hard time calling it what it should be. So when the class is on campus, what we do is you will go to Tyler and say, test me. And you have to demonstrate in front of Tyler that you know how to use a multimeter. So it's kind of like a quiz. And the reason why we do it that way is because otherwise we blow a lot of fuses. But everyone does well after they take that quiz. Okay. All right then. So I'm going to be available from 4:30 to 6 and beyond if need be tomorrow. So please bring your questions. Okay. Same.
Professor?
Yeah.
Can I ask a short question right now?
Okay.
So if there is an electric field, a uniform electric field, and you introduce a charge into the field, the potential of the charge will be due to that field. But then when you introduce another charged particle in the field, would the potential of that charged particle be only due to the main field or also due to the first charged particle that was introduced?
Well, technically, whatever you put in okay, I guess it all depends on the size of the field, the field or potential produced by each charge. I mean, technically, you got to include everything, right?
Yeah, but
Okay.
when I went through it somehow the answer was something like the potential only depends on the main field in which you introduced the particle and not on the other particles which were introduced before it.
Okay, so let's say you're talking about let's say if I put a charge here. Okay, and then I bring another charge, right?
Yeah, there is already a field in which the charge is present.
Okay. So let me draw a field. will draw a uniform field. And let's put a charge here, Q.
Yes.
And then we want to put another charge here, right?
Yes.
So generally, the total field is the sum of these two. The field of these two. But if the field due to the original field is much, much bigger than this field, then we can ignore it.
Okay.
Okay?
Yeah, like I got the answer correct for it, but then when I started thinking about all the effects, I was like, does the other charge do something or not? But okay, we can neglect it.
Yeah, technically it does, but then we can ignore it if it's small.
Okay.
But if you want to do it exactly, you do have to take that into account. But then the problem gets, the reason why physicists want to do approximations is because then they have an easy problem to solve. So physicists do all kind of approximations to make the problem easier to solve, so they get an idea of what's going on. And then once they get the idea of what's going on, if it's worth it, then they'll do a more detailed calculation.
So is like when you introduced the first charge, is something holding it in its place?
Yeah, we're assuming, if it's just sitting there, we're assuming it's being held in place. If it's there and not moving, something's holding it in its place, yes.
Okay, because it was not mentioned that something moved, but then when you put a charge in a field, there's a force on it.
So it's going to want to move, unless
Yeah.
unless there's a second force keeping it from moving. Yeah, sometimes we should be more specific when we.
I don't know, like these days when I look at questions, like weird questions come in my mind. Okay, why isn't this specified?
Yeah, and that's okay to ask, because that would change the problem if the charge is moving, right?
Yes.
Yeah. So it's okay to ask. Sometimes we forget, because there's so many details you have to think about, we'll forget. So like on
Thank
the
you.
exam on Thursday, if you have a question, just go ahead and ask. Make sure
Okay.
that you're answering the right question.
Yeah.
Okay. Other questions?
I have one, but it's not exactly related to what we're doing right now, so I'm going to let everybody else go first.
Anybody else have a question? Now go ahead, Damien.
Have you, and I'm totally out of my league right now, I'm not going to pretend like I know what I'm talking about, but have you heard of the Casimir effect?
Yes, you had Shaquille?
No, I've stumbled upon it just like going down rabbit holes and stuff. The reason I was bringing it up is because you just said the cavity between two conductors is zero, but doesn't that kind of show that it's not?
The Casimir effect?
Yeah, because isn't it like when you bring two conductors really, really close together, something like nanometers apart or whatever, there's like a force between them or something?
Yeah, I don't know I'm not familiar with the details with it, but my colleague, Shaquille, she did her PhD on that.
Oh, really? Okay,
Yeah.
that's funny.
Yeah.
Yeah, anyway, it just came to mind because, like I said, I obviously don't exactly know what I'm talking about, but I know that they're like similar in nature.
Yeah, it has to do with fluctuations within the vacuum. It's a fairly complicated problem, but there's a lot of folks doing research on that topic. I'm just not that familiar. For me to say something very, just to say something very, I don't want to say anything wrong, so I'd have to read up on it. But Shaquille,
Anyway.
if you emailed her, so you had 205 here?
Yeah, I had 205 with Aviva.
Yeah, so you can ask her.
Okay.
Yeah.
Can I ask a question?
Go ahead.
Okay. Like suppose we have two hollow non-conducting spheres, and there is an additional charge placed inside one of the spheres, which is not at the center of the sphere. So the charge would not experience any field from the sphere which encloses it, but there is a field on it due to the other insulating sphere. So in this problem, we cannot use Gauss's law, right?
What is a conductor?
No, both are insulators. But like they're charged.
So you have two charged insulating.
Hollow spheres.
Okay, and inside one of the spheres is the charge.
Yes.
Okay, let me draw a picture. And you have some sort of charge here, Q, right? And okay, so say again what you wanted to do.
So inside, okay, so you have already drawn. So we have to find the field which the charge experiences. Like ultimately we want to find the force on it.
Okay. Yeah, you don't want to use Gauss's law for this.
So can we like simply find the force due to a point charge, which is Q2?
Yeah, this acts like a point charge. Once you're outside, it acts like a point charge.
And the presence of the other insulating sphere has no effect on the field from the other sphere.
Yes.
Okay. Yeah, sometimes it is like hard to accept, okay, no effect is there due to this.
Yeah. No, it's true. Okay, I think I'm going to end it here. And I'm looking forward to see you folks tomorrow night. Like I said, I can go past 6 tomorrow, so. Okay?
Thanks, Professor.
All right. Have a good
Thank
evening.
you.